All right, hey. So write down the following function in your notes. Function looks like this. So write that in your notes. This is just a random function. There's nothing special about it. It's just an example. Just like we just talked about, because it's a formula for a function, we can use the formula to generate a list of xy pairs if we so choose. For example, I could say that f of 0, let's give everyone to get a participation ticket today. So just mentally think about replacing every x with an x value of 0, and just raise your hand when you have the output value. We're just going to wait for the whole room, so like everyone to do it. So plug in the x equals 0 and just raise your hand when you know what the output value is going to be for the y value when x is equal to 0. Call in somebody here in a second. So let's go Autumn.
Oh, 5.
Positive or negative?
Negative.
So Autumn says -5. How many agree with Autumn? Well done. Perfect. Okay. Anybody have a question about that? Awesome. So we can make a table. We could come over here and say x. We have f of x. We just figured out that if we plug in a 0, the output value is -5. We can keep doing it, but it gets rather tedious. That's why I'm grateful that I was born in the era of digital computers, so I don't have to do tedious work so much anymore. I can just pull up some software and let it do it for me. So, but there is one value that we want to investigate today a little bit, and that's if we go to find f of, say, let's see, -4. I need to replace, this is a little tougher, so I'm going to write it down. So I plug in, let's see, -4, square that. Oh, whenever you replace a variable, always replace the variable with parentheses. It saves a lot of mistakes. So it's f of -4. So this is going to be 16. Two negatives make +4. And I get something, oh, the bottom is 0. So I know the value is undefined because whenever you divide by 0, we don't know the result. This one turns out to actually be 0 over 0, which is certainly undefined. In fact, we often refer to this situation where you have 0 divided by 0 as there being a hole in the function. Probably have heard that word before. Questions from anyone? Perfect. So if I come over here and write it in the table, I would have to write -4, and the value is simply undefined. The word undefined literally means this list is the definition of the function. And since the definition does not include any specification for the output when the input is -4, we say that it doesn't have a definition. So we say it's undefined. That's where the word comes from. Questions from anybody? Awesome. Oh, please, Jane. Yeah.
So, like, on the AP test, if we get a question like this, will it ever make us graph any type of chart that has an undefined?
Oh, gotcha. Outstanding question. The AP test is very, how would you say, extremely rare that you ever graph anything. It has happened, but it's really, I'd say, 1%. Like very rare. Once in a while, they'll have you match a graph where it'll be multiple choice. That's easier because you can kind of pick out the right one. But answering your question, again, because a graph is just a picture of the xy pairs, if I'm trying to graph something like this, my graph is just a bunch of dots. And when I get to a place where there's no output, you just don't put a dot. It's really that simple. because there's nothing there. We don't know what the output is. Question? Who else? Cool. Okay, topic for today is this, though. We're going to encounter situations in calculus where we can't be content with simply noting that this is undefined. Like we need more information about what the function is, like what's happening with the function near an x value of -4. So what we want to do is, as best we can, figure out what's happening at least close to x equal -4. So somebody get in on the participation point, raise your hand and tell me, what's an x value that would be considered close to x equal -4? Riley?
-3.
-3. Close is a bit of a relative term, so that's, I call that close for many people. Somebody come up with something that would be closer to x equal -4. So Ken is thinking in a kind of far out there, and she's thinking, well, if I choose -3.99999, and I just keep saying that for the next 3 million years, I get a well, even more than that, right? Forever, I get a value that is, in my head, I can't get any closer. Like if I really go to -3.99999 forever, no value is going to be closer than that. So we're going to write that down. We could write it like this, -3.9 with the little repeating bar over it. But there's another way to write it that I'm going to introduce you to, and you're on the right track. We're going to write it like this. Okay, let's check the whole room for a second. Is the number -3.99999, and I want everyone to answer positive or negative here in a second. Is this number more positive or more negative than -4? Just say it out loud. Positive. Perfect. So another way to write this is -4 with a little plus sign right there. The little plus sign indicates that it's not exactly -4, it's just a bit more. And as Kenneth said, the smallest bit you can possibly imagine, that's how much more it is. Questions? Please, Jake.
The plus arrow means it's a bit more positive than -4?
Perfect, perfect. They do that, Jaden, because we could also do the other way. So Kenneth said one way to get really, really close to -4 is, -3.99999 forever. What's another decimal kind of similar fashion that would also be really close to -4? Or
-4.1.
close, but what is it instead, Andrew?
0 and then 1.
Yeah, there you go. So 4.00000 forever. I don't know how you go forever and then somehow get a 1, because those are kind of incompatible statements, but that's the idea. That number is slightly negative of -4, so we write it like this. Something I like to do in my class is I like to get feedback as to whether I'm on the right track or not. You've done this with other teachers a little bit. It's pretty much what you've done before. But so this idea of, we know x can equal -4. But we also know x can be just slightly infinitesimally positive of -4, or we could have a value that's infinitesimally negative of -4. If that feels really good to you, that makes perfect sense, you're going to do this. If it makes absolutely no sense, you do this. If it's something in between, you can show me something in between. So everybody just kind of silent ballot here, so you don't have to show everybody. Some people are kind of in the middle, a little bit fuzzy still. Just checking everybody in the room. So several people are doing 3s and 2s. So if you can think of something to ask that I think might help me clarify it. If you don't have anything that's popping to mind as far as a question, something that might clarify. Sometimes you don't, sometimes it just feels fuzzy, but yeah, please.
Why is this important to the mind?
Oh, gotcha. So the reason we're investigating it is this. We're going to run into situations where we really want to have a better idea of what the output value is when the input is -4. But we don't know that value. So instead what we're going to do is say, well, if we find what the value is, say, just a little bit positive of -4, like we can find this number, and we can find what the output value is just a little bit negative of -4, that could be useful information. In fact, we're going to come up with the idea that even though this can't be computed, if these two values are known, this value can be basically assumed to be something. Does that kind of make sense? That's the reason why. So, good question. Please.
So how would you graph that point since it's so close to 4? Would you just put like 3.999 in your calculator, just like 4 or?
Oh, very good. Yeah, you can actually use a calculator and type in -3.9999999 into this formula, and it will tell you what the output is quite accurately. On the AP test, they always give these types of questions on the non-calculator section. So we have to learn some kind of logical reasoning techniques instead of just using our calculator. Sure, Trey, you can just plug it in, for sure. Who else? Please, Jake. You're good.
Will there ever be a time kind of like on our quiz where it will ask us like the -4 more negative is less than x, and then x is less than -4 positive? Like,
Oh, like you're saying kind of like, would there ever be some sort of notation like this?
yeah, we're like asking us the rate of change.
Where they want to know what's happening between.
Yeah.
We technically are going to figure out a way to calculate what you're asking,
Okay.
although they won't ask it in the way that you're describing.
Gotcha.
We actually will, in fact, the goal of the whole first semester, it's like, this is very good. The goal of the whole first semester is to gain some understanding and ability to work with this idea. Like, what really is the rate of change between those two very, 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 very close points? Like you have summarized the whole first semester of calculus very well. Like, I'm serious. That's the whole topic of the whole first semester. It's like, how do you find the average rate of change between 2 points that are infinitesimally close? Well done. Well done. And the good news is, even though, like, at a glance, it kind of, like, I'm sensing you all look like, oh my gosh, what do we don't want to do that. It really isn't that bad. Like, the idea is actually quite simple, and it's exactly this. In fact, it's what we've done, where you find the value here, find the value here, and you just subtract. And some mathematicians have come up with some very, very clever shortcuts to make the process really, really easy. Like, without the shortcuts, it's quite difficult. But this class, they don't require you to be good at the hard method. You just have to be good at the easier method, the shortcut method. So we don't really spend any time delving into the details of the more difficult method. We spend all our time learning the shortcuts. So, well done, please.
And also, how do you say that? Like, is there like a name for like the negative and the positive up in the corner? Or like,
Oh, very good. Hold 1 second, I'll explain that in a minute. Very good. Any other questions? Very good. Perfect. Okay, so here we go. So the goal is to figure out this output value and this output value. And the name that Jaden's looking for is, when we go through this process, someone decided that they would call it the process of finding a limit. So write that word in your notes. So they refer to this as the process of finding a limit. I don't know that the word limit fits the situation as well as I would like it to fit, but that's what they need then. Okay, but what you should remember is that finding a limit really is just finding a y coordinate. Like, when we wanted to find f of 0, we just plugged in 0 and figured out what the y coordinate is. When you're finding a limit, what Jaden's talking about, you're still just plugging in a x value and finding a y value. The only difficulty is the x value that you're plugging in is kind of a hard number to work with, because it's like -3.999 forever, or -4.00001 forever. question. Awesome. Next thing in your notes, write this. Here's the mathematical way to write what we're doing. Write the letters LIM. This is an abbreviation for limit. We're talking about what's happening on remember, a function is just a list of x, y pairs. And we're always talking about x and y. So when we're talking about finding a limit, we're doing what Jaden talked about. We're taking an x value. The x value we're interested in is the numbers that are near -4. So we can't put an equal sign here because we don't want x to equal -4. We want x to be close to -4. So the symbol they chose is an arrow to indicate that we're getting close to -4, but we are not becoming -4. Okay. Now, if you want to use arrows elsewhere in your notes, it's actually okay. Because,
I don't use myself.
well, I don't think you will actually. Because it's just when the arrow is associated with a limit sign that means x is approaching. Like I've used arrows for other things, like hey, we go from here to here and just kind of point steps. That's okay. Yeah, you don't have to worry about that. It's just when they use it in conjunction with a limit sign, it means x is getting close to -4. So you asked for a name. There isn't really a name for those numbers, but it's this idea. This is the symbol that kind of means we want x to be either a little bit more or a little bit less than -4. When we're finding a limit, we're dealing with a function. So we have to know what function we're dealing with. So you write down the function as well. So we write x squared, subtract x, subtract 20. The whole thing is divided by x plus 4.
Wait, what?
I heard 3 voices at once. Kennedy, go ahead.
Why are we writing that?
Oh, so back here, we started out by talking about that function, like trying to figure out how it behaves, like find its list, and we're still talking about that function. So the limit, we're trying to find the limit of this function as x gets close to -4. Now, really a better way to say it though, Kennedy, is we're trying to figure out what's the y-coordinate for this function when the x-coordinate's a little bit more than -4 and a little bit less. So we're doing what we wrote in this table. This is just the mathematical symbols that someone invented to mean the same thing. Does that help? Good. Anyone else? Perfect. Write this down in your notes, please. When finding a limit, first, factor and divide if possible. There are a lot of different methods for finding limits. We don't really study limits heavily for this class. We just do kind of introduction. And for all the problems that I've ever seen on the AP test, if you're asked to find a limit, the first thing you want to see if you can do is factor and divide to make the function you're dealing with easier to work with. So don't forget to always factor and divide first. Okay, next thing. Let me make sure we're done with that. Okay. Half of the points you earn on the AP test are in the written section. And so they're grading you on how well you can write mathematical notation. Like, do you write correctly? So the next thing I'm going to do is actually very, very important that you learn to do the same thing. In fact, as time goes by, I will try to check your homework visually as much as I can to make sure that your notation looks perfect. I like to do test corrections. You've done that, I think, with some other teachers sometimes. When I do test corrections, I have you sit right by me, and I literally look at every single line. Because I really want to make sure you don't show up on the AP test knowing calculus and then lose points just because your notation is not correct. Math students are notorious for inventing their own notation. And think of it this way, it's like trying to pass the AP Lit test by inventing your own grammar. Okay, they're not going to really be thrilled about that, so you've got to use the right notation. So we're trying to find a limit. I were working this problem on the AP test, I would not have written what's in green. That's just for your notes. So I've got to declare to the grader that my next line is equivalent to this line. So it's a small thing, but it's actually extremely important that I put the equal sign right there, to indicate that the next thing I write is equal to or the same as this. It's just going to be in a different form. So I write down limit, x approaching -4, and now I want to factor. This is a quadratic, so I do the Mr. Recti hippo butt. Every time I say that, I feel nervous. All right, here's how I factor them. X squared means there's an x here and an x here. There you go. Gotta go take excitement lessons. 20. Okay, I'm going to factor incorrectly to just demonstrate how I think about it when I factor. So when I look at the 20, my first incorrect thought would be, let's see, 20 is 2 times 10. Well, that's right, 2 times 10. So I put a 2 here and I put a 10 here. Okay, on the AP test, I'm showing the grader line by line that this line is equivalent to this line. But I need to do a little bit of scratch work. So I just go off to the side here. And you can do the same thing. So I'm going to multiply this out. So let's see, that becomes x squared. These two multiply to make 10x. The middle terms multiply to make 2x. And the last two terms multiply to make 20 as expected. Okay, I note right away that 10x and 2x will never add to give me the negative x that I need when I'm factoring. So I know that this isn't correct. Questions about that? Okay, so I just grab my eraser and come back over here. Erase the 2, erase the 10. That's just scratch work, so I can just leave that. My next try is 4 and 5. So put a 4 here, 5 here. Come back over to the scratch work. So let's see, that gives me x squared. And then 5x, 4x, 20 again. This one's going to work. So negative goes here, negative here, positive here. So these two now add correctly to the negative x that I need. So now I need to put a negative here, and a positive here. Anyone need me to give more detail?
I missed the part about the 4 and 5. How did you get those?
So like where the 5x and the 4x came from?
From the equation solution.
Oh, from up here.
A little bit longer.
So when I'm factoring, I always look at the first term and I just ask myself, what multiplies to make x squared? So that's an x and an x. Then I look at the negative 20 and ask myself, what multiplies to make 20? I don't worry about the negative yet. So okay, 20 is 4 times 5. That's where they came from. Is that your question? Okay. Anybody else? Awesome. Okay. The value of this limit is the same as the value of this limit. In other words, dealing with this function is equivalent to dealing with this function. It's just written in a different way. But writing it in this fashion allows us to do one more thing. So we write the required equal sign. We're still finding a limit. But now, because this is in factored form means I have one term multiplied by another. These two matching factors can be divided to make one. 1 multiplied by x minus 5 would leave just x minus 5. So the limit, the answer to this limit problem is going to be exactly the same as the answer to this limit problem. Big improvement because this is a lot easier to deal with than all of that. Questions, please, Andy?
Why do you even need to do the limit thing if you can just, like, x minus 5 for a negative 4, it's negative 9. So, like, is that the limit? Or
Yes, but there is a couple of things we got to make sure. Let me just keep talking to you. You're right on the right track. Put this in your notes, please. This has been a mistake over the years that I just don't want you to make, so just write this down. you can only, so you are only allowed to divide if the numerator and denominator are both in factored form and you are dividing common factors. Some people want to take an expression like this and say, well, there's an x in the numerator and an x in the denominator. Why can't I just draw a line through those two and cross them off? You know, let's see, 20 divided by 4 is -5. Why can't I just do that? That's totally illegal. Right? It will lead to the wrong answer 99.9% of the time. So once in a while you luck out, but not very often. Answering Andrew's question, you are correct as far as the manipulation. Like we kind of do this manipulation, plug in the number, we get the right answer. But it's really crucial that the process of finding the limit makes sense to you, like what's really happening. Because again, the AP test writers are just extreme, like they spend a lot of time, they get paid a lot of money to come up with questions that will trick you if you just try to follow steps. So yeah, just stick with me, but you're on the right track. So, we have a question here. So we're trying to find this limit now, which is equivalent to finding this limit. Something interesting happened. We took the x plus 4 and the x plus 4, we divided to make 1. This relates a little bit to what Andrew's talking about. So I'm going to write that over here. X plus 4 divided by x plus 4. And we're saying that that's equal to 1. I'd like to see how many people can read my mind. I look at that and I say, not always. Like, this is usually equal to 1, but there's an exception. There's a case where this absolutely does not equal 1. If you know what I'm talking about, just show me your hand. So you know the participation for the day. What is the value of x for which this does not equal 1? It's super important you note this for the future. What is the value of x for which this fraction will absolutely not be equal to 1? Harder? Negative 4. This is a true statement as long as the x value does not equal -4. We showed that on the last page. If the x value is equal to -4, this doesn't equal 1 at all. It equals undefined. So actually part of Andrew's comment is this. The only reason that this statement is equal to this statement is because we're not ever going to let x equal -4. Otherwise, they're not equal to each other. But when we're finding a limit, we don't let x equal -4, only get close. Does that help a little bit?
Yeah.
Perfect. Questions? Awesome. Okay, next thing, write this in your notes, step 2. Okay, I'm trying to help you understand the general process of finding the limit for any problem that you're going to encounter on the AP test. So we always look to factor and divide first. Step 2 does not apply to this problem, but we're going to write it down so we know how to use it when it does apply. The next thing I look for is check to see if x is approaching infinity or x is approaching negative infinity. So that doesn't apply to this problem because x is approaching -4. It will apply to future problems, and we'll learn how to handle that in another example. So, questions? Oh, please.
Kind of still on step 1. What's the point of getting an x minus 5?
Oh, gotcha. We're getting there. We're not quite there yet. Good question, Solomon. Yeah, step 1, factor to get it into a simpler form. The use of this will show up in a second. Perfect. What kind of helps though is to remember this, Solomon. we keep saying we're finding a limit, but what we're really doing, like I said to Kennedy a minute ago, we're just trying to fill out this table. And we just like to know what's this output value, what's this output value. That's really what we're doing. It's just the notation they use, they say we're finding a limit. Questions? Awesome. Next step. So let's see, let's get another page here. Okay, so we're right here. I'm just going to rewrite this on the next page. You don't need to rewrite it. So we've got the limit as x approaches -4 of the function x minus 5. Okay, the next thing to do is we need to check or find what are known as the left and right hand limits. So find the left and right hand limits. And compare them. If they match, then the overall limit it's a lot of words, sorry. So we find the left and right hand limits and we compare them. If they match, then the overall limit is that value. Otherwise, the overall limit is non-existent. It's a lot of words. I'll take your time to get that written down. So we need to find the left and right hand limits. We compare them. If the left and right limits match, they're like the same value, then the overall limit is that value. If the left and right limits don't match, then we declare the overall limit to be non-existent. Check my notes to make sure I'm not forgetting something. Okay. In some classes I listed as step 3 and 4. I don't really care. You have to do that process. Okay, here's what we mean by finding left and right hand limits. So next page. I do not write an equal sign now because I'm doing a new but related process, so it's not equal to the previous line. I'm finding the left-hand limit. So it's the same function we're dealing with, but instead of x approaching -4, x is approaching just a little bit negative of -4. It's called the left-hand limit because if you if you drew a number line, here's -4. Say -3 is about here. The value that's just a little bit negative of -4 on the number line ends up being on the left-hand side of -4. That's why it's known as the left-hand limit. The other value, so this is kind of the name that Jaden was looking for. Does that make sense? They refer to the other one as the right-hand limit because it ends up on the right side of -4. You do the left-hand limit first. And please, make sure you always do the left and the right-hand limits. That's what I was saying to Solomon. To Andrew. That's a place where they can fool you on a test question. If you forget to do the left and right-hand limit, sometimes you just step in their trap. On the AP test, the multiple choice section, there are 4 answers per question. One of them is correct, the other 3 are traps. They never write a question where the other 3 are like just nonsense answers. The other 3 are always answers that the students logically come up with when they make mistakes. So you have to be really wary of that. Questions?
So if we get an answer that is way off, we know that we just don't get more question.
Sure, in fact, that's actually good news. Like if you're working a problem in the multiple choice section and you get an answer that doesn't match any of them, that's actually not a bad thing because now you can kind of go back and try and find your mistake. The worst thing that can happen, and I'm not telling you to frighten you, but to just make sure you know how it works, is to get an answer because you made a mistake, and they anticipated your mistake. And so they created the answer that's wrong because they knew you might do that. Because then you think you have it right, you just circle the right answers. So they're very good at making sure you really know calculus. Like I had a student one year, quick story. He, to be fair, he was a little bit arrogant, and he just had this mentality of like, I don't need to take notes in class, I don't need to ask questions because I am the world's best guesser. Like when I told him that my tests, like tests 1, 2, and 3 are all multiple choice, the first 3 tests, he's like, oh, hey, if it's a multiple choice test, I always can score well on a multiple choice. I can at least get like a B because it's multiple choice. How hard can it be? I just read the answers, 3 of them are nonsense. I can just kind of logically deduce the correct answer. What he wasn't used to are multiple choice tests where 3 of the answers are traps, meaning they look just as good as the right answer. They're just answers that you would come up with if you make a mistake. He survived the first 2 tests okay. On the 3rd test, there were 33 questions, all multiple choice. He got 3 of them right. True story. Like you cannot survive in this class because you're a good guesser. Okay? It just won't work. Same thing I was saying to Andrew. You can't survive either if you just try to memorize steps. You got to keep digging to make sense of the ideas. Okay, left-hand limit. A limit means we're just trying to find the output value. So now the function's easier to deal with. So we do exactly what Andrew said. We just mentally make a table over here in our scratch work, and we say, okay, trying to figure out what happens to this function when the input value is really close to -4. So let's see, that's -4 minus. So I just plug it in. -4 minus. -5. Now, it doesn't turn out to be exactly -9 because it wasn't exactly -4, but it's really, 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 really close to -9. Please, Jake.
Is there a function on our calculators that gives us the other negative, like the negative in the corner before?
Oh, no. You can do it manually by saying, okay, it's a little bit negative of -4, so it's really -4.00000001. And that would be an approximation. Yeah. Again, they won't let you do that, but while you're practicing, it's not a bad thing. It's a good way to kind of check your work, that sort of thing. So anyway, the value isn't -9, but it's really, 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 really close. When you're finding a limit means what number are we close to? So we're close to -9. So you write down that the limit as x approaches -4. Oh, I did that badly. Sorry. Hold on a second. Don't write this. I did that. Stop there. That's the waste. Apologies for that. Right here, we just want to write this limit's value is equal to -9. Okay? I wrote approximate here because the output value really isn't -9. The output value is close to -9. But when you're writing it with a limit statement, don't ever write the approximate. It's the limit's value is -9 because the word limit means what number are we getting close to? We're getting close to -9. Questions for anybody? Anything that pops in your head, please, Andrew.
How come you don't write -9 minus?
Gotcha. That I've learned from experience, that I don't need to. Like I could spend the time to think for a second, okay, wait a minute. If this was a little bit negative of -4, then yeah, this will be a little bit negative of -9 as well, but I don't need it. So I just don't expend the mental energy to do it. The only exception to that, Andrew, is if we're finding a limit and we end up with a number over here that is close to 0, then we do need to figure out if it's a little bit positive 0 or a little bit negative of 0, since the sign is changing. But here, the sign's just going to stay negative. Good question. Please.
So if you have to find out if it's a little negative or positive 0, when you rewrite it up in the top left, how do you do that?
Oh, gotcha. So up here, it's still going to be equal. Like, because the limit means what are we getting really, really close to. It's just that if there's a need to know more precisely what the output really is, then we've got to think about the fact that we were a little bit negative of -4. We have to think a little bit like Jaden was, that, okay, really, it's negative 4.00001, so this is like negative 9.00001. That's highly unusual. Like, that will happen once in a while, I'd say 2% of the time. The other 98%, you can just kind of not worry too much about it. Good question. What else? Okay, now we need, so that's the left-hand limit. We go find the right-hand limit now. So we say limit, as x is approaching -4 from the right of x minus 5. Mentally, we do the same thing again. We're going to plug in -4, a little bit positive. Subtract 5 from that. And we end up with pretty much the same thing. Very, very close to -9. This one would be a little bit positive of -9, but in the limiting sense, we're getting very, very close to -9. Follow-up questions from anyone? Please, Jake.
Will they always right hand and left hand have the same number?
Awesome question. So back here in our notes, that's why I had you write that otherwise the limit is non-existent. So in this example, they match. And so that means the overall limit's going to be -9 as well. But you will encounter problems. It's actually quite common. I'd say half of them, well, maybe not half, like 25% of the time, they'll give you a problem where the limit is non-existent. So left and right don't have to match. Follow-up questions. So now we write one more thing. We write the overall limit. We say, therefore, the 3 dots arranged in a triangle. It's a legal symbol on the AP test. If you want to write the word therefore, please write it. If you're efficient like I am, I just write 3 dots. Because I get tired of writing T-H-E-R. So therefore, the overall limit, which is the limit as x approaches -4 of this function we called f, that limit is -9. And that would be the answer to this question. And there have been written questions that are extremely similar to this one. Like on the FRQ section of the test, I've seen questions that literally say, show that the overall limit, they actually tell you what the limit's going to be, but they expect you to show that it works out to be -9 by correctly writing the right notation, etc. So, questions from anyone? Please.
Is the therefore important?
Not essential. If you forget the therefore, I don't think they're going to have any read. I was just illustrating the fact that I did mentally compare these two because I know that they are the same. My conclusion is, oh, that means the overall limit is the same. Anybody else, please?
So if this was like a question on the AP test, would this be in the multiple choice or the written section?
Written section. Well, think of it this way, Kyle. I've seen it in the written section where they give you a function like so, and they expect you to prove that the limit is some value. And so they expect you to write these statements in purple. You don't write the green. That was just for your notes. That one we just rewrote it. I would have to show them that the left and right limits are -9, and then have a conclusion in the written section. Probably this could show up in the multiple choice as well. They would just say find the limit. And so no writing is actually required there. I just show you for the written section.
Multiple choice, you could just like potentially just jump balls.
For sure. Yeah, they don't check your work in the multiple choice. It's totally to be there.
On another day, since we are running out of time, will we be taught how to do this backwards? Give someone and we have to prove that if that was accurate, like you were saying before.
Oh.
They might say it's -9 and you have to prove it when backwards.
Gotcha. No, I misled you there. My apologies.
Okay.
You don't ever go backwards.
Okay.
What happens on the written section is once in a while they'll say show the following, which really means they're telling you the result you should get. And so they're saying, hey, we're going to give you the answer. You just show me how to get there.
Okay.
So you actually don't work it backwards. Does that make sense? Yeah, so you would just do what I showed you. Good question. Yeah, when I see an AP test question and it says show, I'm like, oh, good. I know what I gotta get, you know what I mean? It's like I don't have to feel like I'm stumbling around in the dark. They're telling me what my results should be. So that's a helpful thing. Other question? Awesome. Okay, next thing, we got a few more minutes before we pass out the tickets. Okay, back here, look here. It said we're supposed to check to see, step 2 is check to see if the limit is, the x value of the limit is approaching either infinity or negative infinity. So we're going to do another example now. So make sure you don't blend these two examples together. So the other example is actually problem 17 in this packet. So if you want to put it in your notes, that's fine. If you prefer to just use problem 17 in the packet, that's fine as well. Holly will read it to me so I don't have to sit and look at it. So it's some new function. We're finding the limit this time, Holly, of what? And what's the function for which we are finding the limit? Something popped in my head. I need to get that written down, and I'll got to give you a different announcement unrelated to calculus for a second before I forget. So get that one written down, or just use the handout either way. So whichever you prefer as far as organizing your notes. The announcement is, so yesterday we had an evacuation drill, second period. If they ever pull the alarm in this period, let me just show you where you go for my class. Here's a map of the aerial view of the school right here. Very exciting. So here we are in my classroom. If the alarm goes off, we go this way. Okay. So exit the building right here. Just follow the building around. Very exciting. Now here's the crucial part. For some reason, everybody feels like it's some sort of requirement to enter the softball field through this dugout. So there's a really bad bottleneck. No one goes through this one. I don't know why. It's like we're all a bunch of sheep. We just like all the rest of the sheep. So don't go through this one. Come over here. And then you meet me about here, just kind of center field. Just kind of meet me here, cluster around me. I call the roll. As long as you are in class and you show up here, everything's great. If you somehow get distracted and end up not on the roll here, but you were here, I've never actually done this, but I'm sorely tempted to do so. What we do is we kind of make a note of it, and then we wait until the very end of the term, and when everybody else is handing in their tickets to get the extra credit, their grades jumping up by like 1% or so, or 2% or 3%. We say, oh, that's right, you failed the fire drill test. And everyone's like, oh, that's right. And everyone gets this terrible, sad look on their face. And like, oh, so we have to do the fire drill failure ceremony. And we all go back outside, back here. So we come back out here. Let's see. Yeah, we could probably do it. Well, the cars come by there, but we might have to walk a little bit further. We'd probably walk back over to here. It's a good spot here. So as a class, I've never done this, but it'd be very interesting. So if you fail the fire drill, we walk back over to here, and we all kind of make a circle, and we call forth the person who couldn't quite manage to get from here to here successfully, and we have them put their 35 tickets, 3.5% of their grade in a little pile, and then we burn them. So, fire failure ceremony. Weep, sad, grieve the demise of their tickets. So please, no one has ever failed the fire drill, ever. So just make sure you get some. I'm pretty patient, you know. You don't run or you just walk and talk to your friends and stuff, but make sure you show up. Any questions about the fire drill? Awesome. Okay, we kind of used up the time talking about the fire drill. We'll investigate this next time. Let me comment though quickly on this before I pass out tickets. Everybody look at me, please. I want to see your eyes on me. So everyone look up. Everybody look here. Everybody look here. Okay, when you start a class with a new teacher, you're always learning the teacher as well. That's normal. You've got to learn kind of my style so you know how to be successful in the class. One thing I've really tried to reinforce is that I believe strongly that we shouldn't spend really hardly any effort worrying about dishonesty. There's no need. As soon as you take a test, we'll find out if you're dishonest. So that's why you're on your honor to do the quiz in an honest way, grade it yourself, et cetera, okay? Another one of my core philosophies is this. The most important thing about calculus is the discussions we have in class. And really, I want to do as much as I possibly can to help you walk out the door each day feeling, it's hard to be ever 100%, but feeling pretty confident about what we discuss, like it makes sense to you. As I said over and over again, if you're memorizing steps, it's not going to work. So the discussion is super important to me. So I don't ever want to have to say to a student, oh, good question, but we don't have time. Like, you have a question, I want to do the best I can to answer it. Okay, so you feel comfortable. So one thing I do that's a bit different than a lot of teachers is I will often hand out a packet, and then I judge the pace of the class. And kind of depending on the pace of the class, that's how I decide what the homework is. So I often, pretty much all the time, I won't tell you the homework at the start of the class, because that defeats the whole purpose of allowing you to ask as much as you want to ask. Does that make sense? Okay. I keep an eye on the pace. We've got to get to May 15th ready for the AP test. So it's not like you can just keep asking random things. But as long as the discussion is productive and we're making good progress, if we don't get to the homework, I don't worry about it. Do you understand? Okay. We will have a quiz when you come back from Labor Day on Tuesday, like we always do. But this packet, we just didn't get far enough. So keep it, because we are going to use it. I don't want to collect it back. But just hold on to both of these, but there's no assignment tonight other than be ready for the quiz. So it's kind of a nice Labor Day. We're going to pass out the tickets. I sent some presentations. What did you do? I think I did. I really think you don't ask a lot of questions. Some people are just better at listening than they are asking. As far as participation, all I know is when I ask questions that are periodically if you never get called on, that's important.
You're just like
Rock. This is cool.
yeah.
Okay. Told you wheezing. Wheezing. Wheezing.
Every time I cough, I like.
So that's how I'll.
It's a wheezy, wheezy. Tenors of whatever you want. Jackson tenor.
I'm so oh my gosh, and we have to do a whole other.
You're still flat.
It's hard to hold my leg. That's not
Good job, you guys. Come on, please. Good work, you guys. Well done.
Thank you.
You're welcome. Good job, man. Yeah, I did.
Mine's so fun. Thank you.
Good job, Ryan. Well done.
Oh, thanks. I know,
Thanks,
I was
Thank you.
on Tuesday, I like
You're welcome. You're welcome. Good work.
Again, we have a car parked in the west parking lot.
What's up?
Right
All right.
on a dark green Mazda
Good man.
C938SS. Lauren Elliott, David Shippen, Nathan Tillman, and Madeline Johnson. Please come to the main office. Lauren Elliott, David Shippen, Nathan Tillman, and Madeline Johnson. Please come to the main office.
Worries and your strife. I mean the bare necessities or Mother Nature's recipes that bring the bare necessities of life. Wherever I wander, wherever I couldn't be found off my big home. The bees are buzzing